Okay. Okay, so the first topic we're going to cover today is ER diagrams, which is fresh out of midterm 2. That was like the first topic on midterm 2. So we'll do a quick review, and then we're also going to cover other stuff, and especially recovery, because that's the last unit that will be on the final. So for ER diagrams, the ideas are that it's a very high-level conceptual diagram, and it's useful for getting your ideas out about your application, and also it's useful to explain these ideas to someone else who might not be very technical, but it gives you a high-level idea of what's going on in the database, really. And so, hopefully this is all review, but just a quick recap that we have these nouns or entities in our ER diagrams, and we assign them certain adjectives or attributes. And so the entities are boxes, and then the attributes are circles connected to those boxes, or ovals. And then we underline the primary key, right? Okay, so then the next thing we ask is how do these entities interact with each other? And for that we use relationships, which are diamonds, and we connect them to the two entities, or you could have more, as we'll see. And there's also attributes about those, and so you can also connect ovals with attributes to the relationship as well. The last thing we do is we talk about these constraints on these relationships to make the lines in the diagram more meaningful. And so there's 4 different types. We have these key constraints, which are answering the question, at most, how many times must this entity participate in this relationship? So at most infinity, or at most 1. At most infinity is a non-key, but if you say it's at most 1, then you have a key. And then we also have these participation constraints, which give you at least how many. So if you want at least 1, then you're looking at total participation. And if you notice that if you say at most 1 and at least 1, you end up with exactly 1, which is when you get total participation in a key. Right? So that's the basic summary. Do you have any questions up to here? Yes. So the question is, if you have total participation, no, I wouldn't necessarily say that's true. Like what participation constraints are telling you is that this this entity has to be participating in the relationship. So it's kind of like, if you want to make the relationship with SQL, it's kind of like a not null type thing, that this thing has to be filled in. And if it's it may happen to be a foreign key, and okay, maybe that's what you're saying, that in that relationship that it has to be a not null foreign key. Is that kind of what you're getting at? Yeah. Okay, does that make sense? So participation has to do with like it being there, so it being not null. Anything else? Okay, so we'll review some of the more. Okay, so actually, just as a quick recap, I want you to help me out with these true-false, which might look familiar. So the first one is ER diagrams are used to model the physical schema of a database. What do you think? Just shout it out. True or false? False, right? What are they actually modeling? What kind of schema? What's that? Logical or conceptual? That's right. So maybe you aren't super familiar with these terms, but when you hear physical schema or physical things in like systems or databases, you should think of like disks and files and like bits on the disk. And really, that's not what we're talking about at all for ER diagrams, right? We're much higher level. So that's why this is false. Okay, how about this one? An entity set E can be associated with a relationship set R more than once. What do you think? Shout it out. Okay. True? Does anyone have an example? Yes. That's good. Exactly. So my example is very similar. You can be both an employee and a manager, right? They're both employees, but they have that relationship. Okay? How about this one? At most, 2 distinct entity sets can be associated with any relationship set R. False. And who said that? Give me an example. Exactly. So one thing that we specifically covered in lecture is the notion of ternary relationships, where you might have multiple things interacting together, In this case, it's like an insurance example where you have an employee with the policy covering a dependent. Okay? So now we'll move on to some of the more advanced features, which maybe since they weren't hit on in the midterm might show up on the final, and also because you've gotten more familiar with these ideas. So we have this notion of aggregation, so we're connecting stuff together in these relationships, and maybe it's a bunch of entities that are participating as opposed to just one. So my example for you is you might have a worker, which consists of an employee and a job, right? And the worker is what's managed by a manager, not necessarily, maybe you don't care about how the manager interacts with the job and the employee specifically, but like kind of that joint relationship. So what this ends up looking like in the diagram is you slap a box around the thing that you're calling like the aggregated thing, and then that box can be connected to these relationships like that. So does this idea make sense? It's a simple kernel of an idea, just that like sometimes you want to take things up a higher level and group them together, and that's what's participating. Yeah? Okay. So then the other one, which I think you're a little bit more familiar with, is weak entities. And it's this idea that an entity that only makes sense with the parent one, or something that's so weak it can't stand alone on its own. And one example from discussion we saw is maybe you have this idea of trees and islands, and it doesn't make sense to uniquely just talk about a tree, right, because there's so many. But if you have an island, it makes sense to talk about an island like this tree that lives on this island. So what, like a little bit more precisely, what that means is that the key for a given tree is the combination of the island's name and the tree's nickname. Those two together, right? So which one is the weak one, the tree or the island? The tree, that's right. So, and just to be more specific, what does that mean in the diagram? So to make a weak entity in a diagram, you go ahead and you bold the weak entity and the relationship. It's a little bit hard to see here, but tree and is on are both bolded. And then the relationship is going to be many to one. So, the intuition here is that an island can have many trees, but a tree belongs to just one island. So that's that. And then the very last thing is that for a little pizzazz, you go ahead and do a dashed underline on the key of the weak entity. So nickname here has a dashed underline. Does that make sense? Okay, cool. And then the last major skill you need from the ER diagram section is how to convert ER diagrams to entities. And there's just a couple heuristics that you follow. So the E part is easy. For entities, you just convert the columns to, the attributes, which are those like circle things, into columns of your SQL table. And then the underlined one, which we said was like a key for that entity, becomes the primary key in the SQL table. So it looks just something like this. Okay, relationships are a little bit more trickier. So the attributes, so you convert the relationship, again, into a create table with that name, and then the attributes become, they also become columns of that table. The keys, if you think about it, a relationship is specifying how different entities are participating together. So to capture that, the keys of the participating relationships become foreign keys to the entities that they're talking about. So what that looks like for this SQL example is that you have works in, which has foreign keys for the employee's key, which is SSN, and the department ID, which is from departments. Okay. And then the last thing we need to talk about is what about the primary key of this relationship table? And that comes from key constraints on the relationship. So see how departments has an arrow going into manages? So that means that you take the key of departments and make it the primary key of the relationship. So just to reiterate, the key constraints turn into primary keys. Lastly, and this is getting back to the question we had earlier about participation constraints. So when you're saying something must be in this relationship, the way you do that in SQL is with not null. So that says that, hey, this has to be in the table. It can't be a null value. But this is actually pretty limited just because of the way SQL works. It only works under a few certain circumstances, which is like it's a binary relationship with one entity. And does anyone have any idea for why that it doesn't work for like more entities? So it's kind of like a trivia thing, but if you're saying one column, like you say this one must be null, and this one must not be null, and the second one must not be null. You're not saying that. There's no way in SQL very cleanly to say that they both must not be null, right? So like that's why you can only do this for one entity cleanly. Otherwise, you have to use this more advanced feature called check constraints, which we didn't really cover too much. So this is just kind of something you should be familiar with. Okay. So this is So this is what it looks like in SQL. That if we want to say SSN must participate in the works in relationship, we would put a not null here. So do you have any questions on any of the stuff we talked about yet? Yes. Sure. That's a good question. So the question is, why is DID the only thing in the primary key? And it's because if you put the SSN in here, you're encoding something that right. Then you're saying that a department could have two managers, right? Because I could have your SSN in department 1 and my SSN in department 1, and our managers table would have two people as a manager for that department, right? But that's not what this ER diagram is encoding. It's saying that a department is managed by exactly one person. Yeah, and that's actually a way I like to approach these a lot, is just kind of reason through the logic. If you did end up putting SSN and DID both in the primary key, think about what could go in that table, right? You could have unique pairs of SSN and DID, but that implies that you could have two people as a manager for a department. And then you go back to the diagram and you see that's not what the diagram is saying. Yeah. So, and like to boil that all down to like one rule that you can keep with you, the things that are key constraints become the primary key. Good. Yes. Okay. So let's see. Yeah, I cut this off. I'm wondering if there was a foreign key line below this, and I'm guessing there was. So I believe like you could. So all this is saying is that we would want SSN to be a foreign key into this table, but you might potentially have a null foreign key where there is nothing, like it doesn't reach it. There is nothing that matches up. But when we say not null, we're saying you have to have something. This SSN has to participate. Sorry, this works in relationship has to have something from the employee side, which is what the bold line means, right? It's saying that there must be at least one. Let me double check on that if you can have null foreign keys, just because I don't want to say the wrong thing. But I think foreign key really just specifies that this has to come from the other table, right? You say foreign key blank references another table, that the value has to be, like it can't be any value. It has, if there is a value, it's either null or in that other table. Yeah. But let me double check that you can have null. Yes. Oh, yeah? Let me think about that. I'll try and come back at the end and give you an answer for that. Okay. But that's a good question. I'm glad you're asking these questions. And I will say that like converting these to SQL is like an art, not necessarily a science. So sometimes you might have multiple entities in your diagram, but you can have fewer tables if you get the constraints right. It's not like there's an exact translation, but we'll check on that one. So the last thing, I just want to tell you, if you want more practice with these, I think a really good way to do it is to just try, like, this is how you would, if you approach this in the real world, you'd just be giving a list of constraints and have to come up with a diagram from scratch. And your book actually has a couple good examples of these with like some of the more advanced things we talked about, like aggregation and weak entities. So check out these problems in the book and see if you can draw up a diagram. And I did this, and it's a pretty good exercise. But other than that, we'll move on to the next topics, and I'll try and get back to you on some of the questions that came up. Okay. Who's up? Oh, sorry. Okay. So someone just checked more in foreign keys can be null. So that's what that's saying. That it's either null or it's in that table. And then when you say not null, it can't be null. Yep. Varun, you're up next. So next we're talking about functional dependencies and recovery. You're up.
Excellent. Can you guys all hear me in the back? Okay. So I am going to be covering a really quick review of functional dependencies and recovery. Functional dependencies, these slides are kind of based on the slides that I used at the last review session, actually. Even more specifically, they're a strict subset of the slides that I used beforehand. So if you want even more practice with FGs after this, then refer to those slides. All right, functional dependencies. They're written in the form x arrow y. If you say x arrow y, that means that if the x values are the same, then the y values are the same. And x and y over here are sets of attributes. For simplicity, we're not going to use set notation. Suppose we have x is equal to the set AB and y is equal to the set BC. Then we're going to write AB determines BC instead of set A, comma B determines set B, comma C, just to keep the syntax a little bit simple. A little bit more terminology. A superkey is when you can say you have some set of attributes X that determines all attributes of a relation R. Then you say that X is the superkey for R. If no subset of X is a superkey for R, then you can say that X is a candidate key for R. So don't confuse these with search keys for indices. That's a completely different type of key. Some rules for inference if you're given a set of functional dependencies. All of the inference rules can be derived from these three axioms. These are Armstrong's axioms. They're a sound and complete set of axioms, which means that if you have any set, then you can just use these axioms to determine all the possible functional dependencies that you can determine. The first rule is reflexivity. If you have x determines y, and x is a superset of the attributes in the set y, then first of all, that's called a trivial functional dependency. And second of all, you can always say that x determines y. So that's just something that's true. For example, if you have x is equal to like the set ABC and y is equal to the set AB, then that's true just trivially. Then ABC determines AB. The second rule is called augmentation. If you have an initial functional dependency x determines y, and you decide to add the set z to both sides, then you can say xz determines yz, and that's also true. The rule of transitivity says that if you have two functional dependencies, x determines y and y determines z, then you can get x determines z from that. And again, x, y, and z are all sets of attributes. Some more rules that you can derive from these three. You can derive the union rule, which is if you have x determines y and x determines z, then you can sort of combine the right-hand side of those two. You can say x determines the set yz. And the other way around also holds. If x determines yz, then you can break up the set on the right-hand side into two smaller sets. You get two statements that are true, x determines y and x determines z. This is not necessarily true, though. If you have x, y determines y, z, you can't just say, oh, I'm just going to do the opposite of augmentation. I'm going to drop the thing that appears on both sides and get something smaller. You can't actually do that. So you can't say because x, y determines y, z, therefore x determines z. That's not generally true. Okay. Functional dependencies matter because they help with schema refinement. If we look at the definition of Boyce-Codd normal form, we can say that relation R with functional dependencies F is in BC and F if for every functional dependency x determines y in the closure of F. The definition of closure is in the lecture slides. I left it out today just to keep things relatively short. It basically just means that you start with a set of functional dependencies, apply all the inference rules, and then F plus is everything that you can determine after applying the inference rules to the functional dependencies in F. So let's say we do that. Then we consider every FD inside F plus. At least one of the following holds. So y is a subset of x. In other words, the functional dependency is trivial. Like I described earlier, this would be something of the form AB determines B, or something like that. If it's not trivial, then X, the left-hand side of that functional dependency, is a superkey for R. In other words, like if R is A, B, C, D, E, and X is, let's say AB, and you can say AB determines A, B, C, D, E, then AB is a superkey for R. If either one of these conditions holds for every functional dependency, then you know that the relation is in BCNF. The way you decompose into BCNF, there's an algorithm. So just keep repeating this until no FDs inside F violate BCNF. You actually don't need to compute the closure of F, which is kind of nice. So for each functional dependency, if that functional dependency violates BCNF, then you split your entire relation R. You say, I'll take R, I'm going to subtract the right-hand side, and then that's going to be one of my new relations, one of my new tables. The other thing you do is you take the left-hand side and the right-hand side of that FD, put those together, and that also becomes a new table. So you keep repeating this process until eventually you have no FDs that violate BCNF. Okay, we'll step to a practice problem really quickly. If you have relation R with the attributes A, B, C, D, E, F, G, and the given set F of FDs, then ignore the same as before part. I didn't copy the slides correctly, but decompose R into BC and F. So the way that would work is let's go from left to right, dealing with offending FDs that cause us to violate BC and F inside the set F from left to right. So first we'll deal with A determines F. So this violates BC and F because neither of these conditions holds. So it's not trivial, and the left-hand side is not a superkey for R. Because we have A determines F, but from that we can't actually derive any more FDs. We can't say A determines all of R. And because of that, we're going to decompose. We're going to decompose A, B, C, D, E, F, G into A, B, C, D, E, G. We took out F, basically. We took out the right-hand side. And now we'll take both the left-hand side and the right-hand side of that FG, and we'll get AF. We kind of repeat this process. AB determines BC. This one is kind of interesting. I'll get to that in the next slide. But we decompose that in kind of a similar way into ABDEG. And so the relation we're dealing with now is ABCDEG. And the problematic functional dependency is AB determines BC, because it's not trivial, and once again, AB is not a superkey for that relation. So we decompose that way into ABDEG and ABC. And now we still have one problem. We have the FD G determines A, and ABDEG. Again, it's not trivial. G is not a superkey. We decompose again. We get BDEG and AG. And now we have our final answer. These are the 4 relations that we create. And now, whenever we consider any of the FDs that apply to any of these tables from our original set, we'll see that none of them violate BC and F anymore, those 2 conditions listed earlier. And because of that, this is the final decomposition. One thing I glossed over really quickly is AB determines BC. This caused a bit of trouble in the last review session. It's a little bit problematic because we want ABCDEG. It has to split into ABDEG and ABC. And B appears in the first table because we actually deal with this FD in a kind of strange way. We say we split it into AB determines B and AB determines C. This is true by decomposition. AB determines B is trivial, so we just ignore that. And then we're left with AB determines C. So that's the one that we actually use to perform the decomposition. All right, did that kind of make sense? I know I went through that a bit quickly, but I want to spend as much time on recovery as possible. Ordinarily, no. So this one is kind of a weird example because, when I wrote this for the last review session, I actually didn't realize how problematic it was. I guess the real problem is that if you try to apply the rules given the FD the way it is right now, if you say you take ABCDEG as your table, you subtract BC from that, then you'll get ADEG. And ordinarily, you don't need to. It's only a little bit problematic here because B appears on both sides. So then you would have gotten ADEG and ABC. Those would have been the 2 tables that were produced. But then B didn't appear in the first table, and that ended up causing a problem. I realized this during the last review session. I don't remember off the top of my head exactly why it was a problem, but it was. I can tell you that. Yeah.
When you're doing the algorithm to convert to BCNF, do you need to apply the FDs or like later FDs in your set to the new tables that you create?
Yeah, so you consider all of the FDs on every single table that you create. It just turns out that most of the time, the first table is basically R minus the right-hand side, right? R minus Y. And the second table is XY. XY is usually pretty small, so it usually doesn't have too much of a problem. All right. Okay, no more questions? I'm going to go on to recovery then. All right, recovery is all about logging. This is a picture of a log that I took yesterday. It's actually pretty close to where I live. All right, that was actually really useless. I don't know, I thought it was a nice log. So I just took a picture of it. All right, moving on. The recovery algorithm that we use in this class is called ARES. It stands for Algorithms for Recovery and something else that I don't remember. Every single So in Aries, what we're doing is we are creating a log. Every single time that we do an action, we write it to a log. And we don't necessarily do the action because we're using a policy that's known as no force and steal. And more information about this is in the lecture slides. It basically just means that we can do actions, but then they might not necessarily occur on disk. That's where the log comes in. We write it to the log, but we don't necessarily actually do it on disk. So the log record actually reflects what's going on in the database as we perform actions. Each log record has, at the minimum, 4 different fields. The LSN is kind of like an index in the log. It stands for log sequence number. The prev LSN is the previous LSN for that a transaction had when it appears in the log. So the previous LSN is important because if you have actions that are performed by any one transaction, you can follow those prev LSN pointers back in time, and it essentially forms a linked list that leads all the way back to the beginning of the transaction. XID is the identifier of the transaction, and type is any of these types that are listed here. So a log record can have types update, commit, abort, and begin checkpoint, end checkpoint, or CLR. And I'm going to go over each one of these in a little bit more detail. And like this is what the log would look like. Like over here it shows the columns LSN, type, transaction ID, and prev LSN. For update log records, there are actually more fields that get involved. One of those fields is the page ID. That means, we are, like if we look at the first row in this table, we see transaction T1 has prev LSN null, and we're updating the page with PID 1, so P1. So that's essentially what that means. Kind of the same thing at LSN 10. At LSN 20, we're saying, okay, let's commit transaction T1 right now. And the previous LSN of T1 in this log is 0, which you can see just 2 rows above that. Kind of the same thing happens that's continued at LSN 30. We say T1 end. That is the end of transaction T1. The previous LSN was 20, just before that. All right. Whenever we're doing all of these actions, whenever we're logging all these actions to the log on disk, we're also maintaining some data in memory. We have 2 tables called the transaction table and the dirty page table. Transaction table means that it describes all of the transactions that are currently active, currently running in the database. The dirty page table describes the dirty pages in the buffer pool. And the columns of these are as follows. In the previous example, we saw that we had 2 transactions, T1 and T2. But T1 committed. That means it's not actually running anymore. So we only have T2 in this transaction table. The last LSN that it had was 10. Last LSN is just, the last point at which it made some sort of action in the log. And the status is running. The dirty pages right now, let's go back to this case over here. We see that we wrote 2 pages, P1 and P3. We don't know necessarily whether these were actually written to disk. Because of the no force policy that we're using, we don't force them to disk even after a commit. So, page 1, the rec LSN of that thing is 0. The rec LSN is basically just the first thing that made it dirty. The first entry in the log that made that page dirty. And P3 was dirtied at LSN 10. And since both of these occur in the dirty page table, that means that even after all of those actions were executed, P1 and P3 are still dirty. They still exist in the buffer pool. They haven't been forced to disk yet. They've only been logged. Okay, let's go over what it means to commit a transaction. When we say we want to commit T1, what are we going to do in the log? We're going to do 3 things. We are going to, first of all, write all the update log records for T1. So these are just like the writes that are being performed by the transaction. And again, they'll be written to the log, but they may or may not actually be forced to disk, whatever pages are being updated / written. Yeah. Yeah, Aries is always going to be using steal no force. So we write all of the update log records. After we're done with those and we're prepared to commit, we say, all right, we'll write a commit log record right now. So we'll say T1 commit. That'll exist in the log. But we're not done yet. We need to do one more thing, which is we need to write an end log record for T1. And also when we do that, this is the point where we update the transaction table in memory. All right. When we're committing, the actual pages may not be on disk even after the end record. I kind of answered this earlier. The reason that happens is because even after we write the end log record, we're not necessarily forcing to disk. That's because of the no force policy that we're using. And yeah, so at some point those have to be actually forced to disk. That could happen before the end record. It could happen after the end record. It could happen whenever. We don't know. Okay, let's look at aborting transactions. When we do kind of the same thing as before, we write all of the update log records as normal. These are all of the writes that are occurring to pages on disk. These are all of the writes that are being written in the log, and they may or may not be occurring on disk. They may or may not be forced to disk. And then instead of committing, let's say, oh no, something happened. Let's write an abort log record for T1. So when this happens, we have to undo everything that happened that was written, that may or may not have been written by the transaction to disk while it was doing all of these update log records. So for each update that we wrote earlier to the log, we're going to write a CLR to the log. A CLR stands for a compensation log record, and that just means we're undoing whatever may have happened on disk. So for each update that we wrote earlier, we're going to go in backwards order through all of those updates and write CLRs. And then once all of this is done, then we say, okay, there's nothing more to undo, so let's write T1 end and also remove it from the transaction table. Yeah? Sorry? So the things that we're clearing are the T1 updates. So, okay, I guess I was a bit unclear about that. I can update these slides later. But yeah, the things that we undo are for that transaction only. The relationship between this and two-phase commit is, they're actually two different things. Two-phase commit is when two-phase commit is a protocol that you use in distributed systems. Yeah, so two-phase commit is more about consistency. When you have multiple machines that are all kind of, I guess, they'd all be logging at the same time. It's when you have multiple machines and you need to keep things consistent. But when we're dealing with Aries, when we're dealing with recovery, we're worried more about atomicity and durability. So that's what's going on over here. So I guess the answer to your question is two-phase commit exists separately from recovery. They're two different things. The recovery algorithm that you use is basically independent from whatever protocol you're using for distributed systems. Like two-phase commit is a protocol that you could use. Similarly, Aries is an algorithm that you can use for recovery. So yeah, they're completely different. They're completely separate from each other. And you're not responsible for knowing two-phase commit for the final. Question in the back. The question is, does this account for cascading aborts? Again, cascading aborts occur sort of separately from this. So this would be... Actually, wait a minute, no. One thing that we're assuming, at least in this class, is that we're going to be using strict two-phase locking for all of our... for everything related to concurrency control. And because of that, you're actually not going to have to deal with cascading aborts. So when you abort a transaction, it won't cause other transactions to abort as well. You won't have to worry about that. Okay, next slide is... one more question. So how do we go through the updates in reverse order? Yeah, we use the prev-LSN pointers. And that's exactly why we store the prev-LSN pointers in the first place. Okay, checkpointing. At a checkpoint, we dump the transaction table and dirty page table to disk. The time of the checkpoint is defined as the log sequence number of the begin checkpoint record. So essentially, in our log, we're going to have something that says, okay, maybe at LSN 100, we're going to write begin checkpoint. Then we can have a couple more actions after that. And then at some point shortly after that, we'll have an end checkpoint record, which says, all right, we are done dumping the transaction table and the dirty page table to disk. Those are now written on disk. So yeah, we essentially use checkpointing just to make recovery a little bit easier. And I'll get to that right now, actually. So recovery, let's say that we're trying to do some sequence of actions in the log, and we've written them to the log, and we don't necessarily know whether they made it to disk. So we have stuff in the log, and then our system crashes. What are we going to do? We need to recover everything that we had beforehand and continue executing. There are 3 phases of recovery. The first one is analysis. The first thing we need to do is reconstruct the transaction table and the dirty page table. Like I said before, we use checkpointing to make recovery a little bit shorter for us, and this is where that comes in. So we reconstruct these 2 tables using the data that we had starting at the last checkpoint. Once we have our in-memory data working again, we perform the redo phase. This means we repeat all of the actions since the smallest rec LSN in the dirty page table. In other words, we find the smallest rec LSN in the DPT, and we see that, okay, this points to some record in the log, and now we're going to execute everything that occurs after it in the log. We're going to repeat, or not exactly all the actions, we're going to repeat all of the updates and CLRs that occur after that, and I'll get to that in a later slide. Then we have the undo phase, which means we undo all of the actions that were active at the time of the crash. This involves, once again, writing a lot of CLRs, and it's conceptually pretty similar to aborting a transaction. So this is kind of the order that we go in. This is taken from Joe's slides. We start, for analysis, we started the last checkpoint and move forward. For recovery, we started the smallest rec LSN and move forward from there. And for undo, we start at the LSN where we crashed and move backwards through LSNs until we reach the oldest log record of all the transactions that were active at the time of the crash. After that, there's nothing more to undo. Okay. I'm going to have some I'm going to refer to the questions 5, 6, and 7 on vitamin 11. This is the log that was given on the vitamin. You assume that all of these actions occur, and then your system crashes. Essentially what happens is you say begin checkpoint and end checkpoint. This means that everything that's in the database everything that's in memory, the transaction table and the dirty page table, are dumped to disk. We're going to assume that they're both empty, just to make things simpler. After that, we have a couple of updates. T1 writes P1, T2 writes P2, T1 writes P3. These are all written to the log. We abort T1. We undo some of its actions. We write an end T1 record. And then we start updating T2. T2 has a couple of updates as well. It writes to page P1. it starts to commit and then we crash. What's important to note here is that the end record is not written for T2. So let's take a look at what happens there. Analysis phase. We need to recreate the two tables in memory. We scan the log forward from the last checkpoint, which is essentially the very beginning of this entire log. Whenever we see an end record, we remove the transaction from the transaction table. For any other record that we see, so like update or CLR or whatever it is, we use the information in that to update the transaction table. And in particular, if we have an update record, we update the transaction table, but we also have to update the dirty page table. So if the page that is being written is not in the dirty page table, then we'll add it to the dirty page table. Let me think about that. Okay. Wait, you said we can't. Why? So that's true. Yeah, so since you're not redoing any of the actions, yeah, that's right, actually. Since you're not redoing any of the actions, you're not going to be removing things from the transaction table. You'll only be adding them. Yeah. So the redo phase is when you're actually going to repeat the actions. So that's where those are going to come in. As far as I know, during the analysis phase, you can add things to the dirty page table, or specifically, when you see an update record, you can add to the dirty page table, but there's no situation in which you'd remove from the dirty page table. However, you can remove things from the transaction table. I'm actually quite sure about that. Yeah, you can... if you see, because during analysis, you consider every single record that's in the log. So if you see like a commit or abort, or once you see an end record, then the transaction should be... Yeah, if you see an end record, then you should be able to remove it. Okay, yeah. Once you see an end record, then you should be able to remove it from the transaction table. But once you add it to the dirty page table, then it just stays there. That was a good question. All right. Let's look at the vitamin question here. What are the contents of the transaction table and the dirty page table after analysis? We saw that... Let's go back a few slides. So we saw that T1 aborted, but T2 is still going. And we started committing that, but didn't quite finish yet. So T2 is going to be in the transaction table with the last LSN 110. That was where we left off. Its status is committing because it is in the process of committing. The status can be running, aborting, or committing. Those are the three possibilities in the transaction table. Now, as for the dirty page table, we see that P1, P2, and P3 were all written. They were first written at LSNs 20, 30, and 40 respectively. And because of that, these are the values that they're going to have in the dirty page table. Rec LSN is the first LSN that caused the page to be dirty. Okay, let's look at the... Oh. So in this problem, what we did was I didn't actually explicitly say that at the checkpoint the transaction table and dirty page table were empty. We'll be a bit more clear about that on the exam, and we'll actually include the contents if they have any contents. Otherwise, we'll just say, oh, both of these are empty. So we'll be more clear about that. I believe I was more clear on the vitamin too, but I kind of just condensed the vitamin down just to make these slides a bit shorter. Okay, let's look at the redo phase right now. So we scan the log forward from the smallest rec LSN in the dirty page table. We're only concerned about updates and CLRs. For each record that's of one of those two types, we repeat it unless one of these conditions occurs. If the affected page is not in the dirty page table, that means that whatever operation was supposed to happen to it, well, it's not dirty anymore. So we don't repeat that. We don't actually make it dirty. If the affected page is in the dirty page table, but rec LSN is greater than whatever LSN we're on right now, whatever we're repeating right now, that means that the first thing that made that page dirty is after this LSN. So again, we don't actually worry about it. And the third condition, we're actually not going to be testing this because this is just too complicated. This means if the page LSN, which is in the database itself, on the actual physical page on disk, is greater than or equal to the LSN of the action that we're executing right now, then we are not going to be repeating that. And this one is actually more complicated because it requires I/O. So it's actually slow. And it's kind of... So we didn't touch on it too much in this class, so don't worry about that particular case too much. Going back to I just made the slide wrong, but oh well. Vitamin 11, what are the LSNs of the redone actions? These are the LSNs of, well, let's go back to the slide over here. So the smallest rec LSN in the dirty page table is 20, right? So this is where we start. And if we go back to the log, we're going to look at all of the updates and all of the CLRs that occur starting at that number. So those are 20, 30, 40, 60, 70, and 100. I believe that's everything. And 20, 30, 40, 60, 70, 80, and 100. 80 is nothing. Don't worry about that. So these are the ones that we're going to redo. Now for the undo phase. The undo phase is where we actually where we start writing new log records. So we don't write any log records to the log during analysis or redo, but during undo, this is where we have to actually start writing CLRs. The algorithm is, we start with a set. Let's call that to undo. It's the set of the last LSNs of all transactions in the transaction table. And while that set is not empty, we're going to perform a bunch of updates here, lots of iterations. We're going to remove the largest LSN from to undo. We'll get some log record that way. If that log record is a CLR, the type is CLR, and the undo next LSN is null, then there's nothing left to undo. We write an end log record for that transaction. If it's a CLR record and the undo next LSN is not null, undo next LSN indicates where you have to go backwards to undo that record. Then we add undo next LSN to our set to undo. And if neither of these are true, so we're not dealing with a CLR record at all, and we're going backwards, like following all of these prev LSN and undo next LSN pointers backwards in time. We're going to, first of all, add the prev LSN to our set to undo. And in particular, if it's an update record, then we're going to undo that and also write a CLR to the log. This is the point where we actually write a log record. So we can write either a CLR record while we're dealing with updates, or we can write an end transaction record after there's nothing left to undo and we've gone all the way back to the beginning of the transaction. So conceptually, it's very similar to aborting that transaction. One edge case regarding undo that we weren't very clear about in lecture. Suppose we write a commit record and then we crash. This is exactly what we're doing on the vitamin. No end record was written, and the transaction is actually in the transaction table created during the analysis phase. Its status is going to be committing. We saw that a couple of slides ago. So, since it's in the transaction table, by the definition of the toUndo set, since we start with the last LSNs of all transactions in the transaction table, we actually have to perform undo on that transaction. Even though the commit record was written, even though kind of conceptually it seems intuitively like it should be done, but we're not actually done. The reason for this is because of one particular case in distributed systems. So if we're using two-phase commit, the end record indicates that two-phase commit got a decision to commit. It's separate from the commit log record. And you don't need to worry about it too much for this class, but that's the reason why. So if you see a commit record and you don't have an end record, then you still have to undo that during recovery. Okay, I think this is the last slide. What are the contents of the table after undo? We'll see that we have to undo. We already saw earlier that we had transactions T1 and T2. T2 had already aborted. T1 had already aborted, and we'd written an end record for that. And this happened before we crashed. It happened after the checkpoint, but before the crash. And because of that, we're not going to be undoing it. In the transaction table, we do have transaction T2. So this is the one that we have to undo. So we're going to write CLRs for all of the actions here. We're going to say we'll undo the action at 100, which is some update. We're going to undo the action at 30, which is some update, and then we'll end the transaction. And if we, oh God, here we are. Yeah, so these are the updates. We have update T2 writes P1 at 100. If you go back, we jump up to here at 30. T2 writes P2. That's another update. And that's the other one that we undo. And then we write the end record, and that's it. Okay, that's all I have.
All right, guys. Very cool. So we have a lot of stuff to get through. So I'm gonna fly through this a little bit. So we're going over text search and concurrency. So just as a refresher, when we're doing text search, what we care about is answering queries like this one. So we have words in our queries, Berkeley, awesome, so on and so forth. So we want to find documents that contain these words. So the way that we model this is that we have a bag of words, right? So every document is just some some set of words. But when we're constructing this bag of words, there are two key ideas. The first is that you stop words. For example, the word the or this are very commonly used, probably not very helpful in searches. Second idea is that you stem words. So for example, if you're searching for the word surfing, you're probably okay with the word surf as well. So you don't necessarily so you'd rather keep the root of the word rather than the whole word. So the way we're going to do this is in a relational database, for example, you'll have a relational text index, right? And this what this is going to be represented as a table. It's going to have a term, for example, Berkeley or surf or whatever it is, and that's going to be mapped to a doc ID. And so now you can do single word queries really easily, right? Because all you're going to do is select star from inverted files where text is equal to whatever the word you're looking for is, right? So that's pretty straightforward. If you want to do multi-word queries, then you can union multiple single-word queries, right? So if you want Berkeley and computer science, then you'd search for Berkeley, you'd search for CS, and you take the union of those. If you want both, then you take the intersection, so on and so forth. So here's an example. Boolean search in SQL. It's pretty straightforward. It's going to look like this. Any questions about this? Cool. Okay. So so if you want the exact phrase, so for example, if you search for Berkeley database research, right? The way everything we've described until now would just give you all words that contain Berkeley and database, or all documents that contain the words Berkeley and database and research in no particular order. Berkeley may be the first word, database may be the last word, research might be somewhere in between. But what we really care about if we make this query is probably, can I get Berkeley database research here as a phrase or super close by? So if you want the exact phrase, what you're probably going to do is something like the position of Berkeley is going to be one less than the position of database, which will be one less than the position of research. Or perhaps you want them to be near each other. So you'll make sure that the difference between the distances is less than some threshold k. And that'll give you documents where Berkeley database and research are all close to each other. So there are two. We've figured out how to find documents with queries, right? But if we're really doing, like building a search engine, we actually want to be able to rank these things. So there are two kinds of ranking. There's classical IR ranking, where every document is represented in the vector space of all words. So if there are 250,000 total words, then you represent every document as a vector in 250,000D. Where its distance in each dimension is how many times it contains a particular word. So you normalize your vectors, otherwise longer documents will inherently be more similar than shorter documents. So there's this whole idea of cosine similarity here, and the way cosine similarity is going to work is pretty simple. You're just going to take your normalized vectors, and you're going to compute the cosine similarity of the two. It's just like simple math, and we're not going to ask you to do like complicated math on the exam or anything, so don't stress too much about that. But yeah, if you're wondering about the formulas, they're all in the lecture slides or in section slides, so you can look there. The other thing, a little bit more, perhaps a more modern algorithm for this is TF-IDF, and what TF-IDF is it's the for a particular term in a document, TF-IDF represents the value, quote unquote, of that term in that document. So TF stands for term frequency. It's the number of times the word occurs in a document. And IDF stands for inverse document frequency, and it's going to be the log of the total number of documents divided by the number of documents with this word. So basically the way you can think about this is like how valuable or how rare is this word, right? So if this word is in 2 documents out of 10 million, then its IDF is going to be really, really high, which means it's a really uncommon word. Whereas if you have the probably appears in every document on the internet, so its IDF is going to be 0 or pretty close to 0, right? So yeah. So if we're indexing by TF-IDF, just the last conceptual thing, you're basically going to add a table to our schema, the whole inverted files thing we were talking about earlier, and it's going to be the term info, and term info is going to be a text and the number of documents that contain this word, and that's the denominator of IDF. And then we're also going to add this float that's doc term rank, which is going to be the TF-IDF of a particular word in a particular document, and that's going to be added to the end of our inverted files table. Any questions about that? Cool, okay. So since we only have 15 minutes left, moving right on, we have transactions. So transactions are basically a sequence of reads or writes on database objects that must commit or abort as an atomic unit. That means is that either the whole transaction happens, every read and write in that set happens, or it does not happen. You can't have half a transaction happen. So so like we covered earlier, we want to maintain these ACID properties: atomicity, consistency, isolation, and durability. What atomicity means is what we're just talking about, that either all actions in a transaction happen or none of them happen. What durability means is that the effects of a committed transaction must survive failure. So that's what Varun was just talking about with the recovery stuff. Even if the database fails after we say transaction is committed, then it must have committed. We can't lose the the data from that transaction. Consistency just means you want to preserve your integrity constraints. So if you say that your balance of your bank account can never be less than 0, then you don't want to allow 2 simultaneous transactions to withdraw $100 from an account that only has $100, right? Because then your total bank account balance would then be less than 0. And the last thing is that isolation basically means that every transaction should basically, like the results of every transaction should be executing them by themselves in some serial order without anything else going on. So everything we're going to talk about is in terms of enforcing mostly like atomicity, consistency, and isolation. The durability stuff is covered by Aries. So conflict serializable schedules enforce isolation, and they're a subset of all schedules that are basically a conflict serializable schedule is a schedule that is conflict equivalent to a serial schedule. A serial schedule is just a schedule in which you do like T1, then T2, then T3, like some sequence of transactions. What conflict equivalence means is that if they have the same actions of the same transactions the conflicts occur in the same order, right? And so, for example, if transaction 1 is doing a write and transaction 2 is doing a write, and the write of transaction 1 comes before the write of transaction 2, then there must be some serial schedule in which all the conflicting actions of transaction 1 come before the conflicting actions of transaction 2, right? And if that holds true, then the schedule is conflict equivalent to some serial schedule, and it is therefore conflict serializable. So conflicting actions are actions from different transactions on the same object, and you must have at least one write, right? So either they're both writes, or one is a read and one is a write, because what you read would depend on whether the write comes before or after that read, for example. So those are things that constitute conflicting actions. And yeah, so this is what we just went over. So the way that we can deterministically figure out if a schedule is conflict serializable is by drawing this dependency graph. And what we're going to do here is we're going to put one node per transaction, and we're going to draw an edge from Ti to Tj. If there's some operation in Ti that conflicts with some operation in Tj, and the operation in Ti appears in the schedule earlier than the operation in Tj, right? So basically what that means is that Ti, in our proposed theoretical serial schedule, Ti must come before Tj because its action comes before, right? And so if there is a cycle in this graph, that means that, let's say there's a cycle between Ti and Tj, that means Ti must come before Tj, and then Tj must come before Ti in our proposed serial schedule, but that can never be true. They can't both come before each other. So if there's a cycle, then it's guaranteed that the schedule is not conflict serializable. And if you are into theory, you can prove that if there is no cycle, then you're guaranteed that it is conflict serializable, but you can just take that at face value. Right, so this stuff is just identify a conflict serializable schedule if we give you one such schedule, but we haven't actually told you how you generate one of these schedules. So what we're going to do is, the way we're going to go about doing this is through locking, in particular two-phase locking. And I'm sure all of you are very familiar with this by now, but the way this works is that you have an S lock, which is a shared lock, which means that which means you're going to read this, and you're going to have an X lock, which means you're going to write to this data. And the main big idea of two-phase locking is that you have an acquisition phase and a release phase, and that means that once you release a lock, you can't acquire any new locks. Because the second you release a lock, the acquisition phase is over, and you must now proceed to the release phase. But the one big thing here is that this doesn't prevent cascading aborts. If you're confused about why that is, look through the lecture slides or watch the webcasts. So the way we're going to do this is by doing strict two-phase locking. This is going to prevent cascading aborts. It's the same thing as two-phase locking, but the key difference here is that the release phase only starts at the transaction commit or abort point. You can't release any locks until you write your commit record or write your abort record. So that's locking. This strict 2PL prevents cascading aborts, and it produces conflict serializable schedules, which is exactly what we want. But it doesn't prevent deadlocks. So if you look in the lecture slides, there's some stuff about deadlock detection, deadlock avoidance, and then like how you deal with deadlocks. They have these like very pleasant algorithm names called wound, wait, and wait die. Very uplifting. But yeah, so like review that stuff. It should be pretty straightforward. One of them, they basically prefer or give priority to older transactions over newer transactions. Okay, so last 10 minutes we're going to go over the advanced concurrency control stuff. Like Joe said in lecture last week, the only stuff that we're going to require you guys to know from this is multi-granularity locking, which really is pretty straightforward, and time-ordered multi-version concurrency control. Everything else, latches, B-link trees, the phantom problem, what else do we cover? Weak isolation, snapshot isolation, all of that stuff you don't need to know. These are the only two things that you need to know. So we're going to go over that real quick. So multi-granularity locking is pretty straightforward. Basically, if you think about it this way, if you're writing to a database, you don't want to get an X lock on the whole database. That would be ridiculous because then no one else could touch any of the data in the database, and you've basically made your system serial, right? Complete waste of time. So instead what you're going to do is you're going to have locking at multiple levels. So for example, you may have the database level, at the table level, at the page level, at the tuple level, right? Those may be your levels of locking. And basically, unless you're going to write to every single tuple in the database, you're not going to get an X lock on the database. If you're only going to be updating one particular tuple, then you'll get an IX lock on the database, you'll get an IX lock on the table, you'll get an IX lock on the page, and then you'll get an X lock on the particular tuple that you're updating, right? And it's the same thing. You're basically these intention locks, so IX means intention for an exclusive lock, IS means intention for a shared lock. All that means is that you're going to say, I'm going to actually get this kind of lock at a lower level in the database, at a more fine granularity than the one we're currently at, right? So this is the lock compatibility table for multiple granularity locking. It's probably a good thing to like put down on a cheat sheet. It doesn't take up much space, and it's pretty useful. The one mildly confusing thing here is the SIX lock. So it's a shared lock on the whole level that you're at, and it's an intention to write at a more fine level, right? So basically, you can think of this like maybe you're going to scan the whole database and update some tuples. So you're going to read the whole database, so you'll get a shared lock on the whole thing. But you're only going to update some of the tuples, so you don't want to get an X lock on the whole database, but you want to get an IX lock because you're going to get an X lock at a finer granularity. So yeah, any questions about that? Yeah. So that means that you can think about it this way. So if you have an IS lock, then you can get another IS lock. But if you have an IS lock, you can't get an X lock, right? So basically, you can think of the column is like what you already have, and the row is what you can get, or vice versa. Yes, at this level of granularity. This is at one level of granularity. Cool. Anything else? Awesome. Okay, yeah. Oh, I guess I skipped all of this. Okay. So TOMVCC. TOMVCC is basically going to be based on this idea that every transaction gets a unique timestamp. Every action that this transaction takes is going to be marked by this timestamp. Even if we've moved on 150 timestamps from when this transaction started, it's going to be marked by its original timestamp. And for each data item, this might be a tuple, this might be a page, it depends on the implementation, you're going to maintain a set of read timestamps, and you're going to maintain a set of versions. The version is just a write timestamp and the value that was written at that write timestamp. And the basic algorithm here is that reads are always going to succeed. When you do a read, you will all that's going to happen is you're going to go to the versions, find the version with the greatest timestamp less than your transaction's timestamp, and you're going to read it, right? There's never any conflict, always going to succeed. Writes fail if there is a timestamp that happened in between the write timestamp and the next write, the next write after the write that we are, right? So if we're T1 and we're timestamps, we can draw it out. So if we have, yeah, that's terrible. if we're T1 and we are at, well, so these are our writes and these are our reads, right? And so there's we're like T1 has timestamp 65, right? So let's say that there's a write at 75, right? And we're T1, and we're going to try to do a write at 65, right? So the question here is there a read that happens in between these two writes, right? So if there's no write now, there's no read, so we can put a write here, right? And there's no issue with that. But the issue is if there was a read here, let's say at 70, right? If there was a read there, and then after that read happened, we came and inserted this write at 65, we would have essentially changed the past. Because what should have happened was, in a consistent universe, the read at 70 should have read the version at timestamp 65, but because it got inserted after the read at 70, it would have read the previous version, wherever that was, we don't care, it would have been the earlier version. So what we've done here is we've effectively changed the past, and that's the only thing that we can't do. So this is the only case in which writes will fail, right? And the reason that we only care about this interval right here is because if this write had happened at 80 instead, then this write doesn't affect that because it would have already read the version at 75, and this made no difference to it. So that's the one situation in which writes will fail in TOMVCC. The main idea here is that locking is expensive, so you're going to try to let the transactions run without locks, and then if there's a conflict like here, that's when you would abort a transaction instead of having this expensive locking for a lot of situations in which you don't really need to lock. Okay, so that's the gist of advanced concurrency control. We're out of time, but we'll be here for a few minutes if you guys have any questions, want to talk about anything. And good luck on the final, guys.